Hello students. So there's just one last thing that I want to do. I want to prove that this sequence of functions converges uniformly in order to give you an example of proving that a sequence of functions does in fact converge uniformly. So claim 4.1.5, the sequence of functions given by g sub n of x equal to sum from k equals 0 to n of x to the k converges uniformly to 1 over 1 minus x on the closed interval from negative a half to a half. And well, let's do it. As a starting point, let's remember that the finite sum, g sub n of x equal to the sum from k equals 0 to n, is given explicitly by 1 minus x to the n plus 1 divided by x, whenever n is equal to 1. I don't remember if we actually gave a proof of that, but the proof is, straightforward enough. You can prove it by induction if you want. You always have that option. But let's use that to prove the claim. So if I want to prove something about uniform convergence, I need to prove that for every epsilon something happens. So I need to start with consider any epsilon bigger than 0. I will let big N be something that I get to choose. I'll consider any little n bigger than big N and any x in the closed interval from negative a half to a half. Then, I want to show that this sequence of functions converges uniformly to 1 over 1 minus x. So I need to show that the limit minus the function is straightforward enough. But this function, g sub n of x, has a fairly explicit definition. So that's 1 over 1 minus x minus g sub n of x, but I know that g sub n of x is equal to that. So that minus 1 minus x to the n plus 1 all over 1 minus x. Well, simplifying that, right, you see what's going to happen. I'll get a, well, okay, so we can get a common denominator. 1 minus 1 plus x to the n plus 1. When I say we can get a common denominator, we already have a common denominator, so it's easy to subtract these fractions. And, well, you see that the 1 minus 1 will cancel. So let's simplify that a little bit. That'll be absolute value of x to the n plus 1 divided by the absolute value of 1 minus x. All right, so let's think about this. So x is between negative a half and positive a half. And let's go off to the side, maybe even see what that means. So if x is in negative 1/2, so this is a side part of the proof. I just need to figure out what goes in this blank. Negative 1/2 less than or equal to x less than or equal to 1/2. So I want to know where x minus 1 lives. So x minus 1 will be somewhere between negative 3/2 and negative 1/2. And notice that 1 minus x is in the denominator. I would like to make the whole thing bigger. So I want to make the denominator itself smaller. So what is the smallest that denominator can be? It looks like, so everything here is negative, right? Negative, negative, so this has to be negative. So 3/2 is bigger than or equal to the absolute value of x minus 1 is bigger than or equal to 1/2. So the absolute value of x minus 1 is at least 1/2. What does that mean? So that means that this whole thing is less than or equal to the absolute value of x to the n plus 1 divided by 1/2. Maybe we can simplify that a little bit to 2 times absolute value of x to the n plus 1. And you know what? Let's not use that just yet. Again, since x is in negative 1/2 to 1/2, I can control the thing in the numerator. Absolute value of x is less than or equal to 1/2. That's less than or equal to 2 times 1/2 to the n plus 1, which is 1/2 to the n. And I know that I'm going out of order according to the steps, but that's okay. That's less than 1/2 to the power big N, since little n is bigger than big N, and, well, I haven't chosen big N yet, but I think we're ready to. If I solve that for big N, well, that would mean 1 over epsilon is equal to 2 to the big N. So looks like log base 2, 1 over epsilon is equal to big N. We'll do the job. So I'll set big N to be log base 2, 1 over epsilon, which will result in this being equal to 1 over 2 to the log base 2 of 1 over epsilon, which is equal to epsilon. Summarizing, this means that for every epsilon bigger than 0, there exists a big N, so that for every little n bigger than big N and every x in the closed interval from -1/2 to 1/2, we have that the difference between the alleged limit and the function g sub n of x is less than epsilon. This means that g sub n converges uniformly to that limit. Groovy. So I hope that this one in particular helps while doing the homework problems in which you will prove that certain sequences converge uniformly. Wonderful. I'll talk to you in a little bit.